All right, so look up at the screen here. We have a 45-foot tall steel sculpture, and that's made from 10 tons of steel. That's a lot of steel. If a proton had the same mass as the sculpture, then an electron would have a mass of about 5 kilograms. So what they're saying is, look at how big and massive this thing is. An electron is so much smaller. It's about the size of a paperclip. So this is a 45-foot steel thing. That's very heavy. It's 10 tons. And a paperclip is not 10 tons. So that's an example of comparing the mass of a proton to an electron. So electrons are very, very small compared to protons. So today we're going to talk about protons, electrons, and neutrons and subatomic particles. Protons, based on the experiments, Rutherford concluded the amount of positive charge varies among elements. So different elements had more of a positive charge and some had less of a positive charge. A proton is a positively charged subatomic particle that's found in the nucleus of an atom. Each proton is assigned a charge of +1. Each nucleus must contain at least one proton. So hydrogen is the smallest atom that we got, has one proton in it. Electrons are negatively charged subatomic particles that are found in space outside of the nucleus. Each electron has a negative charge of 1. Okay, and this is Thomson's work. So positive charge comes from Rutherford. Thomson has the negative charge. It's interesting that the charges are equal even though there's such a discrepancy or difference in the size of the mass. Right? In 1932, Chadwick carried out an experiment and showed that neutrons exist. Okay, Chadwick concluded that the particles he produced were neutral because the charge object didn't deflect their paths. So neutrons could be fired through a slit experiment, and the positively charged plate and the negatively charged plate had no impact on neutrons. So he said that must be a neutral charge. So a neutron is a subatomic particle that is found in the nucleus of an atom, and its mass is it's pretty close to a proton. It's a little bit different, but it's closer to a proton than it is an electron. So what are the properties, and how can we compare the properties of protons, electrons, and neutrons? And how can we, tell the difference? Well, we're going to talk about mass, charge, and location in the atom. So the symbol for an electron is E with a little negative sign. All right, you'll see me write that on the board from time to time. What's the charge? -1. What's its mass relative to a proton? Well, it's almost 1 over 2,000. We said that yesterday, right? It takes 2,000 electrons to make up the same mass as a proton. Actually, it's 1,836. The actual mass is 9.11 times 10 to the -28. On the worksheet we did yesterday, they said what's the difference between the particles, and one of the options is color, and somebody thought that the color coding meant that they were different colors. That's just how the book makes it easier for you guys to distinguish. Electrons are not really yellow, okay? But the textbook is going to use yellow to represent an electron always, okay? A proton, P with a plus sign, showing that it has a positive charge of 1, its mass is 1.674 times 10 to the -24. And in your textbook, it'll be green. A neutron is just N, no plus or minus, because it's a neutral charge. It has a charge of 0, and it's so close to the size of a proton that we don't worry about it. So it's a little bit bigger, just barely, okay? And in your textbook, it'll be purple. Protons and neutrons have almost the same mass. About 2,000 electrons equal the mass of one proton. However, an electron has a charge that is equal in size to, but opposite of a proton, and neutrons have no charge. Protons and neutrons are found in the nucleus, while the electrons are found in the space outside of the nucleus. And they're kind of like in orbitals or clouds, and we'll talk more about that later on. So, how are atoms of one element different from atoms of other elements? And atoms of different elements have different numbers of protons. So that's the question. They're asking a question, that's the answer. Okay. So the atomic number of an element is the number of protons in the atom of that particular element. All atoms of any given element have the same atomic number. Each hydrogen atom has exactly one proton in its nucleus. Hydrogen is assigned the atomic number 1. Okay. Each element has a unique atomic number. So each element here has a different atomic number. So sulfur is 16. Now, if I say the atomic number for sulfur is 16, what does that tell you about the atom? What is the atomic number equal to? The number of protons. So when you see that its atomic number is 16, we know that it has 16 protons in the nucleus. It probably has 16 electrons, too. The atomic number for iron, which is interesting, it's Fe, is 26. So how many protons are in iron? 26. The atomic number for silver is 47. How many protons? 47. How many electrons then? Probably 47, right? Because they like to be balanced. Atoms are neutral, so each positive charge in the atom is balanced by a negative charge. In other words, if you have 16 protons, you probably have 16 neutrons. If you don't, there's some wonky business going on. So hydrogen has an atomic number 1, so it has 1 proton, therefore it also has 1 electron. Sulfur has an atomic number of 16, so that means it has 16 protons, which means it also has 16 electrons. Now, we talked about this yesterday. The mass number is the sum of the neutrons and the protons. All right? Now, it's pretty close, well, unless you get to the bigger elements. But a lot of times, you got the same number of neutrons as you do protons. But as you get to the bigger elements, you have more neutrons. And it's an average. So the atomic number of aluminum is 13. That means it has 13 protons and 13 electrons. And the number of aluminum has a mass number of 27. So if you take 27 and minus 13, that tells you you have 14 neutrons. So as you start to get into the bigger elements, it may vary a little bit. The neutrons do is the protons have positive charges. So they can't get real close together because they'll repel and fly away. But if you put a neutron in between, I'm going to use my coffee cup. Look, if I put this coffee cup here and I put the 2 protons together, that neutron kind of acts as a buffer. Okay. That way they don't fly away. That's how they're able to stay so close and dense in the nucleus of the atom. That's why they're necessary. So what is the difference between 2 isotopes, I always say isotopes, of the same element? Well, an isotope is an element that has the same atomic number but has different mass numbers, so they have different numbers of neutrons. So enriched uranium is an isotope, and they have to enrich uranium. So for nuclear reactors to make electricity, they just don't pull up any uranium out of the earth. They actually enrich it and add a couple neutrons to it. Adding the extra neutrons makes it not quite, I don't want to say unstable, but it makes it, when the reaction takes place, more likely to split apart. So you'll see that in the news sometimes. Countries will be enriching uranium. By the way, it's the same type of uranium they use in a nuclear bomb. That's why everybody's so nervous about it. Isotopes are atoms that have the same element and have different numbers of neutrons, therefore they have different masses. So if you look on the periodic table, carbon is 12.0001 or something like that instead of just 12. That's because when you take a sample of carbon, every once in a while, instead of having 6 neutrons, one might have 7. Or they might have 8. Carbon-14 has 8 neutrons. It gets bombarded by some subatomic particles from the sun, and that's how we do carbon-14 dating. To distinguish one isotope from another, the isotopes are referred to by their mass numbers. So oxygen actually has 3 isotopes that exist in nature. Oxygen-16, that's the normal one. Oxygen-17, that has 1 extra neutron. And oxygen-18 has 2 extra neutrons. All three oxygen isotopes can react with hydrogen to form water or combine with iron to form rust. With most elements, it's hard to notice any differences in the physical or chemical properties of their isotope. Hydrogen is an exception. Hydrogen has no neutrons, none. It only has one proton, so it doesn't need any buffers. Hydrogen 2, though, does have one neutron. So there's hydrogen 1, hydrogen 2. Hydrogen 3 has 2 neutrons. Now, a lot of these isotopes come from the fact is that the sun emits a lot of subatomic particles, and they just collide into the elements on the Earth, and they wedge neutrons into those elements. And that's why carbon-14 dating works. Eventually, those extra neutrons, they just don't like being there because they don't really belong, and they start to decay. When they decay, which takes a long time for carbon-14, 5,700 years is the half-life. Then you can tell how long something's been on Earth. There's a lot of assumptions for that model, but that's how it works. But when you do that, because hydrogen's so small, if I add a neutron, it almost doubles the mass. If I have 2 extra neutrons, it could triple the mass. So it does have a change on the mass, but the elements and the properties are based on the charges. So it only has 1 proton, so it pretty much acts like hydrogen. So what do we notice about water that contains these isotopes? Well, because they're heavier, it's going to do something differently. So look at this. If you have ordinary water, that's hydrogen 1, it will boil or have a melting point, not boil, it will melt at 0 degrees Celsius. But if it's a little bit heavier water, it takes a little bit more energy for it to melt. Does that make sense? Boiling, the same thing. You got to go a degree or so higher to boil. The density is different too because the mass is different. Remember, the density is the mass over the volume. But it averages out. You'll have hydrogen 1 mixed in with hydrogen 2 and so on and so forth. Real quick, answer these questions. In which way do isotopes of an element differ? What do you guys think? C, the number of neutrons in an atom. That's the only difference in the isotopes. Of the 3 atomic particles that form an atom, the one that is the smallest is the neutron. True or false? Which one's the smallest? It's not the neutron, it's the electron. So that's false. Okay, that's it, guys.